So again, thanks for the invitation. I will be talking about frequency and cardinality recovery from sketches, which is kind of a niche problem, and it's been mostly developed in the machine learning community. So I will try to give you an overview of why it is important and what is this topic about. So the setting is that we observe a sequence of tokens or symbol that I will call xi. And this take value in a, let's say, countable universe of symbols. So for instance, we have here that x1 is a blue dot, then x2 is a red star, then there is the orange thing, and then again, there are these symbols that are repeating themselves. You can think of these symbols as words or n-grams, that is n sequences of words, or URLs or IP addresses. The main idea is that the data set is huge. So we are possibly in a streaming setting. We have no idea how big is this data set. And storing the frequency of each token is impractical. So we cannot save the whole data set. We cannot say x1 is equal to this, x2 is equal to that, but we cannot even store, let's say, there are 3 blue balls, 1 red star, 1 orange pentagon, because the number of unique symbols is too large. And in this setting, people have been developing what is called data sketching. So a sketch is a compressed representation of the data in the same way that a sketch is a summary of a painting, you can imagine. And you build it with a random hash function. So you have this random hash function, h, that goes from the universe of symbols to the set of integers from 1 to capital J, and capital J can be fixed by the user. And so when you want to sketch the data, you first initialize a vector of zeros in memory that is as long as capital J. This will be the sketch CJ. And then what happens? You start with the first element, you see it, you pass it through the hash function. So here, for example, h of x1 is equal to 2, and then you go in position 2 of this vector and you increment by 1. You do it for the second vector. So for instance, for the second element, so for instance, h of x2 here is equal to capital J. So I go to the last element of this vector and I increment it by 1. And here is when things start to get tricky, because when I do it for x3, then I have that h of x3 is equal to 2, which is the same value that h of x1 was taking. So I have 2 different symbols, the blue and orange one, that get mapped by the hash function to the same value. So here I'm losing some information. And anyway, once I've done it for all my data set, I have this vector of counts that I will call the sketch, where each entry records how many times I have seen a symbol that gets mapped to this particular value by the hash function. And now we consider 2 inferential problems, which is not really related to inference, but we call it recovery problems. The first one is a frequency recovery. We have a new token that arrives. So for instance, we are talking about words. The n+1 word is hello. We have already sketched the whole data, and we want to understand or estimate how many times we have already seen it. So we want to estimate the frequency of xn+1. And of course, this is a recovery problem, meaning that if I had access to the whole data set, this wouldn't be a problem at all. I would just need to be counting. The problem arises from the fact that I don't have any more access to the x1 to xn. I only have the sketch and xn+1. And the cardinality recovery, instead, you have this vector of size capital J, and you wonder how many distinct symbols are there. So can I estimate the size of the seen universe? And again, I need to provide an answer using only the sketch. So in particular, I will be focusing on the first problem here, and maybe talk a little bit about the second problem in the simulations, but this can be tackled using analogous techniques. So as I told you, these problems were very popular in the computer science community, especially in the beginning of 2000, due to computers not being big enough to store physically all this data set. But nowadays, even though actually having a memory issue is a non-existing issue, meaning that we can store basically any data set, people are still using this representation of the data due to privacy concerns. So it's a very actual problem that many tech companies are facing. And so since it was developed in the computer science literature, the main approaches that have been considered were algorithmic ones. And the most popular one for the frequency recovery is the count mean sketch developed by Cormod and one of the students in 2005. And the idea is to have not just one hash function, but have capital M hash function. So when I start processing the data, I map it with M independent hash functions. And then when I want to predict the frequency of xm plus 1, what do? I go through my hash functions. So h1, for instance, I map xm plus 1 via h1. And for instance, here, it gets mapped to the value j. And in the first row, in position j, I have the value 19, meaning that with the first hash function, I've seen 19 symbols, 19 times a symbol that gets mapped to the value capital J. And so I save it in this position of the vector and do it for capital M hash function. And for instance, for the capital M1, xm plus 1 gets mapped to the value 2. I go in position 2 of the last row, and it gets mapped, and I recall here 630. And these are upper bounds on how many times I've actually seen xm plus 1. And the count mean sketch algorithm just output the minimum of these upper bounds. Of course, this is, again, an upper bound, but it has quite surprising performance guarantees. And in more recent year, people have been trying to improve on the count mean sketch, mainly from a statistical point of view. So the point here is that data in the algorithmic approach are considered fixed. There is no structure on the stream. While if we are statistician, the first thing that we want to try is to add a model to the data and see if this improves on the estimation. And so in particular, in this paper by Kai and co-authors, people have been modeling the data stream as a sample from a random probability measure. It means that there is a random probability measure P, such that given P, X1, Xn are IID P, and P is distributed according to some law. And then they consider what they call a posterior. Then we will show that this is not actually a posterior, but still is the probability that I've seen Xn plus 1 equal to R time, given the same information that was going into the count mean sketch algorithm. And since the hash functions are independent, this is the product of some single hash posterior. So it's a probability that xn plus 1 is equal to R, given that in a compressed version, I've seen the compressed version of xn plus 1 a certain number of times. And this approach then has been extended to deal with other class of priors, such as the Pitt-Major prior, to deal with power law streams, which are the most commonly employed. So the first thing that we must notice here is that basically here, this is the main goal of the inference. Then we just take a product and we are done. And the first question that I ask myself is this a real posterior? Meaning that if I go back to the previous slide, I have that I have a matrix of size m times j, while here I'm conditioning only on, well, here m numbers on the left-hand side, and here on one number instead of n times j numbers. So is this the real posterior? And to answer this question in a work that is now on arXiv, written together with Stefano Favaro, we assume the same model as before, but with a broad class of priors, namely the Poisson-Kingman prior, that I won't go into too much detail here, but it's a very flexible class of priors that includes the Dirichlet process, the Pitt-Major process, and the normalized generalized gamma process as special cases. And one of the main results is that we provide an analytic expression for what we call the real posterior. So this is the probability of having observed xn plus 1 equal R times, given the whole sketch. And as we can see, it's not so simple here. So the first thing is that this is a very complex expression that, well, here it looks like a simple thing, meaning that it depends on a couple of functions. But the problem here is that computing this function has a complexity that scales exponentially with the sample size. So we are basically dealing with a useless expression, meaning that it's meant to be dealing with large data set, but can only tackle very small data set. When we specialize the case to the Dirichlet process prior, then some magical cancellation happened, and we have that the full posterior that we computed is actually the fake posterior, or the single number posterior that I was mentioning before. So in a sense, the approach by Kai and co-authors, where they assume the Dirichlet process as prior, is fully Bayesian, meaning that they are actually using the full posterior to derive inference. It's only through sufficient statistics. But the negative answer is that we can characterize the Dirichlet process as the only random probability measure in the Poisson-Kinman class for which these two expressions coincide. In all other cases, which are maybe more suited to model the dataset, we have that we cannot actually compute in a reasonable time the resulting expression, which makes the Bayesian non-parametric approach, let's say, of limited utility. And so we tried exploring a frequentist setting in a work written by me, Stefano Favaro, and Matteo Sesia, which is still in preparation. So here we are just assuming that there is a probability measure that its fixed is the unknown parameter, and that data are IID from this unknown probability measure. And so if P is known, then we can compute this probability here, pi j, that is exactly the probability of having observed xn plus 1 r times given the whole sketch. So this would be, if we were taking like an expectation with respect to the law of the random probability measure, this would be the full posterior. Now instead we are fixing one particular distribution. And once we have these quantities here, we can take the expected value of this distribution and say that this is the natural estimator of how many times we have seen a particular symbol. And what is interesting is that in this result, we have an explicit characterization of this quantity, which, unlike in the Bayesian non-parametric case, depends only on one single bucket of the sketch. So it doesn't depend on the whole sketch, just on one bucket. So these are good news. The bad news is this depends on this probability distribution, which is the conditional distribution of what is going on between all the values that are mapped into the jth bucket by the hash function. And so this is exactly something that we cannot have any information on, since we are hashing the data and we have only information on how many times we've seen a symbol xi that gets mapped to the value j. And so how do we deal with this? How do we estimate these unknown quantities, given that our data does not inform about this? So the first thing that we tried to do was a worst case analysis. So without going into too much detail, the worst case analysis defines a parameterized family of estimator, and then finds a suitable upper bound for a risk that holds for all the distribution in a certain case, and then finds the best estimator that minimizes this upper bound on the risk. And the result that we obtain is a rather discouraging one, meaning that we have that the estimator that we obtain is equivalent to the one of the count mean sketch algorithm. So basically now we have gone back from where we started. We started from the original count mean sketch. We have tried some things like Bayesian non-parametric approach. This was too computationally demanding. Then we tried the frequentist approach. We had to estimate some quantities. We used a very refined technique on worst case, and then we go back to the original count mean sketch. And so our insight was that choosing a single probability measure and taking the worst probability measure was maybe too hard. And instead, what was probably a better option was to smooth this estimator, meaning taking an average of this estimator over a suitable class of plausible distribution, calligraphic P. And in a sense, this can be seen as an analogous of the Bayesian approach, where we have a prior that says which are the probability measures that are plausible. And here we have a very general result that says that if the plus the plausible probability measure, the class capital P here, is the one of normalized random measures with independent increments, we have that the object of inference here, that is the expected value of the frequency, has a simple expression, meaning that is a mixture of binomials, where the probability of success here has a certain distribution that depends on the Levy intensity of this normalized random measure, but in several cases can be computed rather easily. And let me say that this is very different from the Bayesian non-parametric approach. So the Bayesian non-parametric approach first considers the posterior of the random measure given the sketch, and then averages with respect to this posterior the estimated frequency. Here instead, we are averaging not with respect to the posterior, but with respect to the prior, but we are not averaging the frequency of xn plus 1, but rather this functional that is derived, that makes sense since we are using this result here. That is, if I knew P, this would be the estimator on how many times I've seen xn plus 1, and then I average this estimator with respect to the prior. And so we have considered several cases, in particular the Dirichlet process and normalized generalized gamma process. Under the Dirichlet process, we have a very simple expression. Under the normalized generalized gamma process, again, it's a rather simple expression where here we have only the exponential integral function, which can be computed by standard software packages. And we did some experiments where we show that basically the normalized generalized gamma process does a better job at the frequency recovery problem. And as I said in the beginning, we also have the case for cardinality recovery problem. And here again, we show that the normalized generalized gamma process does a better job than the Dirichlet process when there is data generated with a power law. In the few minutes that I have left, let me just mention that all of this was done dealing with one single hash function, but in the original count-mean sketch algorithm, we have capital M of them. So can we deal with this too? And is there any advantage in having more than one hash function? And to do so, we take inspiration from the multi-view learning literature, in which you have data that are represented using multiple views. For instance, you have an image and a caption. They talk about the same thing, it's just two different kinds of data. In our setting, we see each of these rows as a view of the data set. It's a compressed view of the data set. And we consider, for each view, we have an analytic expression for the conditional distribution of interest on how many times I've seen xn plus 1. And we consider two rules to aggregate these conditional distributions that I will not talk too much into details, but the first one just takes a product of all these conditional distribution. The second one is it's a bit more refined and deals in its analogous of the count-mean sketch where we take a minimum. It's just a probabilistic minimum here. And interestingly, if we take the first kind of rule and we apply a Dirichlet process muting, we obtain the same posterior as in the original paper by Kai and co-authors. And if we take the minimum of expert rule and we apply a worst case analysis, then we recover the original count-mean sketch. And again, we have some experiments where here I'm varying the number, the width of the hash. So how many functions is an inversely proportional to this? I'm keeping the memory fixed, so the number of hash function decreases as the axis x increases. And what is interesting, in my opinion, is that in the last case we are using only one hash function. And we see here this error, so the lower the better, that it's always better to have more than one hash function, even if the total memory is fixed. So in conclusion, I think that in this work, we have provided a statistical framework for the analysis of a sketch data. And the nice thing about it is that in order to have something that works both conceptually and also practically, meaning that we have some estimators that can be computed, we had to combine frequencies and Bayesian non-parametric approach. We have many more simulated examples in our paper, where we show that the smoothed estimator do have very good empirical performance. And as I mentioned before, there is the whole cardinality recovery problem that I have not mentioned in this presentation, but it's present in the paper. So thank you for your attention. I'll be glad to take any question.
Thank you, Mario. Is there any question? I have one. So you consider the expected value with respect to normalized random measures, and how do you select the hyperparameter?
Yes, so this is a very good question. We use an empirical Bayesian procedure here. So the idea is that using this smoothed estimation is, in some sense, is still assuming that there is a Bayesian model underlying.
Okay.
So it's still assuming that
it's very different from the Bayesian approach. So you can apply
yes.
still the the empirical.
Yes. So like the main insight here is that this is still assuming that there is a Bayesian model of this kind. It's only that we are not considering the posterior distribution, but only the prior. And so since we are using the prior, it's legitimate to optimize with respect to the parameter of the prior in an empirical Bayesian framework, and we maximize the log likelihood of the sketch data. Or if we have access to some initial part of the stream, we save it and optimize with respect to the marginal distribution of the first part of the stream of tokens.
Okay. Did you try other procedures or not? Only the empirical based procedure?
We tried in this Beraha and Favaro paper here to optimize with respect to the prediction error. So we treat it as a problem, a prediction problem, where we have some sort of function that is the posterior law of our induced by our prior that depends on some parameters, and then we have some training data. And this functional parameterization depends on the parameters of the prior, and we try to minimize the prediction error. But it seems like it's actually pushing all the parameters to have a very low number of unique values, since this is like the sketch on the first few unique values, first few data is not representative of all the sketch, of the remaining sketch. So there is some problem here in this optimization procedure.
Thank you. Andrei?
Thank you. Again, we stimulate a lot of questions, so please ask also participants others. My question relates, you use normalized generalized gamma process, and I have seen in the simulations that you even left out fit manure, if I see so correctly. So what is the advantage of this gamma process to pit manure, say? How can they be compared? Thanks.
So yeah, sorry, for the sake of time, I didn't talk about the simulation stuff, but we use a pit manure process to generate the data. Instead, if we wanted to use a pit manure process as a smoothing distribution, then we would be kind of in some problems here. Because these results here only holds for normalized random measures with independent increments, because at least before normalization, we need to have that evaluation of this measure on disjoint sets are independent. This is what allows us to take into account only the jth bucket and not the whole space. And instead, for the pit manure process, you design it in such a way that you break this independence assumption. So we cannot deal with the pit manure process, and the NGG is surely a bit more complex, but should do the trick with the power law distribution. So that's why we use it so much.
And are there significant improvements in the NGG over PY?
So we cannot actually use the PY to estimate things, because the main result doesn't hold for the pit manure. So we have no idea on how the expected value of Pj of Rp is behaved when P is distributed as a pit manure process. If data are generated from a Pitman-Yor or normalized generalized gamma process, I would say that these graphs would look like the same. Like the only thing that matters here is the discount parameter or tail parameter of the Pitman-Yor process. So the heavier the tail, the more it is difficult to estimate things. And this would be the same if we use an NGGP to simulate the data.
Okay, thanks.
Okay, thank you. Any other question?
Can I ask a slightly more trivial question, maybe?
Yeah.
In the beginning of could you maybe go to the first or second slide? I just wondered, is there any connection to clustering? Because the problem that you mentioned here seemed awfully similar, because that's all about grouping as well.
Yeah, so the problem, the main difference here is that these clusters are imposed by some random hash functions. So they do not describe any similarity between these objects. While in clustering, you would try to find meaningful groups of objects. While here, you could think of this as URL addresses or like random things that do not carry any meaning. So here is a blue ball, but it's not
So
that
you can't
if
really
I
make
had
any sense of their connections, or?
Yes, exactly.
I understand.
Yes.
Thank you.